Okay, so let's start. So in the last class, towards the end, I was discussing this problem of source coding, wherein you want to compress a memoryless source. So it's basically a sequence of IID random variables, an n-length sequence of IID random variables, with each component being distributed according to some PMF Px, and we want to compress it to the minimum rate. You want to represent it using just NR bits in a way so that you can recover xn with high probability. Right? The probability that xn hat, the recovered version, is not equal to xn is called the probability of error. And using concentration inequalities, I didn't give a complete proof, but I sort of gave a sketch to show you how to derive exponential bounds on the probability of error, right? And I didn't really discuss the rate here because recall that the scheme was the following. You consider this set T epsilon, which is the set of all sequences for which the frequency of occurrence of each letter is close to the actual probability of that particular letter, because we know the actual distribution from which the source is generated, right? So the rate is basically equal to log of the size of this set T epsilon divided by n, and the probability of error, as we saw, is exponentially decaying in n, provided of course that you fix epsilon. If epsilon is fixed to be some arbitrary constant, then this becomes, then the probability of error is exponentially decaying in n, and it's also exponential in epsilon square. All right, so I won't discuss the rate, how do you compute the rate, but it's not very hard to do so. You can compute the exact size of epsilon in terms of the binomial coefficients. Basically, it's a set of all sequences for which the frequency of occurrence is within a certain range, and you can express that just for example, as you did in the first assignment, to count the number of sequences, number of binary sequences having exactly p1s is basically n choose np, right? So similarly, the number of sequences for which the frequency of occurrence of character I is ki is basically just the multinomial coefficient n factorial divided by k1 factorial, k2 factorial, k3 factorial up to k8 factorial, right? And you can use Stirling's approximation to basically get a bound on this particular size. As it turns out, again, I leave it as an exercise, you can show that this is roughly equal to the entropy of the source. If you choose the set in this particular form, this particular set has size very close to 2 raised to n times the entropy. So the rate is very close to the entropy. Now, in information theory course, you may have seen this set. Have you seen this particular set? When you discuss types or the typical set, right? Again, there are different versions of the typical set. So if you've seen this particular version of the typical set, then probably you would have seen a proof as to how to bound the size of this particular set. One way is probably the method, the Cover-Thomas method. The other way is you can write sort of a complicated expression for this, an exact expression for the size of T epsilon as a sum of various multinomial coefficients, and even you can bound the coefficients using Stirling's approximation, and it turns out to give the same quantity, right? So yeah, long story short, the rate of this particular scheme turns out to be very close to the entropy, within an epsilon of entropy, and the probability of error decays as 2 raised to minus some constant times n times epsilon square. All right. So this was just to give a flavor of how you can use these tail bounds to obtain bounds on the probability of error. And these are commonly used in compression, communications, and so on. Right? And we'll see other applications as well. So far, we've basically seen some basic tail bounds, Markov's inequality, Chebyshev inequality, and the Chernoff bound. The Chernoff bound is basically the strongest, but sometimes it's complicated to use. But then for certain classes of distributions, like sub-Gaussian and sub-exponential distributions, we can obtain exponential tail bounds for these kinds of random variables. And these cover a very large class of random variables. So using these techniques, basically we can obtain tail bounds, sometimes exponential, on individual random variables x and maybe sums or linear combinations of IID random variables, right? And we've seen at least 2 or 3 applications where the problem can be basically reduced down to analyzing tail bounds on sums or linear combinations of random variables. We saw the Johnson-Lindenstrauss lemma, basically dimensionality reduction. We saw this problem of source coding, and in your assignment, you have a problem of analyzing the probability of error of a randomized algorithm, right? But in many applications, it's not possible to express the quantity of interest as a sum of random variables. Right? What if it's a more complicated function? Correct? So ideally what we want are tail bounds on slightly complicated functions, more general of, let's say, a sequence of n IID random variables. So I have a sequence of n random variables, and I want a tail bound on some complicated function of these n random variables. And the kind of functions I have in mind are not like square or exponential or anything like that. They could be like really complicated to describe. For example, I could be interested in the largest eigenvalue of a random matrix. Right, so let's suppose that I have an n by n matrix where each entry is drawn IID according to some particular distribution, and I want a tail bound. I want to somehow bound the largest eigenvalue. Can I do that? Now, this, I don't even have a closed form expression for the largest eigenvalue, right? But still I want a tail bound. Or I could have a function of the following form. Suppose I draw a random graph, okay? Consider the Erdős-Rényi graph, wherein I have a graph, and every pair of vertices is connected with probability p and not connected with probability 1 minus p. Maybe what I want to do is analyze the maximum degree of this random graph. Right, again, that's not a simple, so you can't really express it as a sum or linear combination of these IID random variables. It's a much more complicated function. All right, and many such functions for which I don't have a closed form expression in terms of these random variables. But of course, it can't be an arbitrary function, right? Because then we can't really hope to derive a suitable tail bound. So we need some restrictions on these functions. And the kind of restrictions that we look at are, so we want these functions to be not influenced too much by any single random variable. Any single xi cannot, if I arbitrarily change any one xi, the value of these functions can't change to a large extent. So for example, if I take the largest eigenvalue of a random matrix, if I just perturb one particular entry of this random matrix, then the largest eigenvalue does not change by a significant amount, right? If I don't perturb it too much, if I just perturb one variable, then if I just perturb one entry, then the largest eigenvalue does not significantly change. And similarly, if I take a random graph, right? Suppose each pair of vertices is connected with a certain probability p. If I, let's say, delete one particular edge or add one particular new edge, then the maximum degree does not change much. It can at most change by 1, right? So for these kinds of functions, we want to derive tail bounds, right? So this is a very large class of functions. But as it turns out, for many such functions, you can still derive, in fact, exponential tail bounds. Yes.
If the function is depending mostly on one single variable, can we just assume it to that in that variable?
Which you could, again, you could, but one feature that they somehow want. Okay, so what you're saying is a valid point. Suppose that you have n random variables, and let's say it's significantly influenced by one particular variable, right? You can derive a tail bound, assuming that the most of the influence is taken by this random variable, and the contribution of the rest of the random variables is significantly small, right? So you can derive an upper bound, but for such functions, the probability or the tail bound that you derive will be almost independent of n, correct? But in this case, as it turns out, for such functions, you can derive tail bounds which decay exponentially in n, and that is extremely useful in a large number of applications, right? So basically, all of these are useful in sort of the large system limit, where n is typically large. You have a large number of vertices, or you have an n by n matrix where n is sufficiently large. So that's sort of the regime that we're interested in. Any other questions? Okay, but even before we sort of derive tail bounds, for such functions, it's, in fact, forget tail bounds, even forget deriving exponential tail bounds, deriving any sort of a tail bound is not very easy, right? Because for some of these quantities, we don't even know what the expected value is. So ultimately, all we can say is that the deviation from the mean is, we want to prove that the deviation from the mean is not too large, right? And sometimes even computing the mean may not be very easy. And in fact, we'll see a bunch of examples once we go into it. We'll see a bunch of examples where we don't know the actual mean, but we can still derive a bound on the variance, or basically a tail bound, right? So in order to do this, we'll need some sort of additional tools. But before that, let's try to see what makes the difference between functions of random variables and sums of random variables. So suppose I have n random variables, x1 through xn, and I'll define z to be some function, let me call it g of x1 through xn. Now, if this function is basically the sum of these and all the random variables are IID, what can I say about the variance of z? Sorry? So the sum, I'm not taking the average, but the sum. So it would just be the sum of the variances of the individual random variables, right? As long as they're independent. I don't even need identically distributed. So the question is, the sort of way forward would be, can I somehow express the variance of this z for a general function g? Can I express the variance as a sum of variances of some random variables each random variable essentially capturing the influence of maybe one of these components, right? You'll get what I mean by that. Okay, so I have this particular expression. I'll define a new random variable zi as the conditional expected value of z given x1 up to xi. Okay, so effectively this is just integral. Again, it's an n fold, it's a n minus I fold integral of g of x1 through x1 up to xi, xi plus 1 up to xn, f xi plus 1 up to xn given x1 up to xi. Right, so this is the quantity that I have in mind. Okay. If all the random variables are IID, then basically you're taking the expectation of z with respect to xi plus 1 up to xn. Okay, the last n minus I random variables. Okay, this again, we'll have a bunch of notation, so it's good to understand what each quantity means. All right, so zi is basically, I have n, it's a function of n random variables. So zi is a function of x1 through xi, and it's obtained by averaging out z with respect to the last n minus I components. All right. Okay, so what would be z0? It's just the expected value of z. x1 up to xn, right, which is equal to expected value of z. What is zn? Just z, right? So it's just, so you're remember that zi is obtained by averaging out the last n minus I components. So zn would simply be, you're not averaging out with respect to anything, so it's just z. So this is f of x1 through xn. Correct? Now, if I had to express the variance of z, or the variance of f of x1 through,
It will be G.
which one? Sorry, right, it's g the function is g. So if I had to express the variance of g of x1 through xn in terms of the zi's, what would that be equal to? So it is the expectation of z sub n minus z0 the whole square. Right, that's fine. Okay, now let me look at this. So the quantity of interest is basically zn minus z0 the whole square. right? Let me see if I can express Zn minus Z0 in some particular fashion. So let me take Zn minus Z0. Can I say that this is equal to summation I equal to 1 to n Zi minus Zi minus 1? Just take a moment to pass this particular quantity. So this is equal to Zn. I'm starting from n, let's sort of coming down in the reverse order, coming from n to 1. It's basically Zn minus Zn minus 1 plus Zn minus 1 minus Zn minus 2 plus Zn minus 2 minus Zn minus 3 and so on. It's a telescoping sum all the way up to Z1 minus Z0. So all the terms except Zn and Z0 get cancelled out. Okay. So the variance of Z is essentially equal to expected value of summation I equal to 1 to n Zi minus 1 the whole square. Zi minus 1 this whole square. The sum the whole square. Okay. So let me call this quantity Zi minus 1 delta I. Right, so it's equal to expected value of summation I equal to 1 to n delta I the whole square. Which is equal to expected value. If I expand this summation, take the square, this is equal to summation I equal to 1 to n delta I square plus summation I equal to 1 to n summation j equal to 1 to n but j not equal to I delta j, right? So effectively this is just equal to summation I equal to 1 to n summation j equal to 1 to n delta j, but I'm separating out the components, that the i's and j's which are equal and those which are not equal. Okay, but I can also write this as sort of summation j equal to I plus 1 to n 2 times, right? So I'm just playing around with these quantities, right? So in case, now again I'm trying to express this as a sum of random variables, and if these random variables were independent and 0 mean, then this quantity would be equal to 0, correct? And I'd basically be left with expectation summation I equal to 1 to n delta I square, right? If the delta i's and delta j's were independent or at least uncorrelated and 0 mean. So let's look at each of these delta i's and delta j's to get a sense of what they mean and how they behave. Okay, so let me call this equation 1. So this is also, I have this particular expression for the variance. Let me look at each delta I. So delta I is basically Zi minus Zi minus 1, correct? And recall that Zi is expected value of Z given x1 up to xi, and Zi minus 1 is expected value of Z given x1 up to xi minus 1. right? But I can also express this in terms of zi. So again, let's consider the case when all the x1 through xn are independent and identical. Okay, let's just say independent. Forget identically distributed. This is basically, so this is essentially equal to expected value with respect to xi plus 1 up to xn of z. Correct? I'm averaging with respect to xi plus 1, xi plus 2 up to xn. Whereas in this case, I am averaging with respect to xi plus 1 up to xn. Right? So can I express zi minus 1 in terms of zi? Exactly. Right? So zi minus 1 is expected value of xi up to xn of z, which is the same as expected value with respect to xi, expected value with respect to xi plus 1 to xn of z, right? Which is the same as saying expectation with respect to xi of zi. Right? So effectively each delta I is equal to zi minus expectation with respect to xi of zi. Is this fine? So what is expectation of zi of delta I? And you're taking the expectation with respect to all n random variables. Just to make it more precise, expectation with respect to xn. In fact, I only need to take expectation with respect to the remaining random variables. I've already essentially taken the expectation with respect to the first I minus 1 random variables already. So what is this expectation equal to? It's equal to 0, right? In fact, expectation with respect to xi of delta I, what is that equal to? 0, right? Because it's just expected value of zi minus expected value of expected value of zi, which is just expected value of zi minus expected value of zi, it's equal to 0. So this quantity equals 0 for all I. So that's a useful property because I know that each of the delta i's has 0 mean. Now, what about a delta I and delta j for j greater than I? So let me consider a j which is strictly greater than I. I want to know what happens to expected value with respect to xn of delta I, delta j. I will assume that all the xi's are independent. In fact, a lot of these, you can get all of these even without independence, just using properties of the conditional expectation. So now let's assume that all the xi's are independent. So this is expected value with respect to xn of, let's recall what delta I is. It is just, let me see, expected value with respect to x from xi plus 1 up to xn. I'll denote this x subscript I plus 1 superscript n is basically xi plus 1 superscript n is x I plus 1 up to xn. Okay, I'll just use this particular notation just to make things more convenient. Of z minus expectation with respect to xi up to n of z. So it's zi minus zi minus 1 times expected value x j plus 1 to xn of z minus expectation x j n of z. So in fact, let's maybe look at an even simpler quantity, which is just the expectation of delta I delta j with respect to just xj. Okay, I'm assuming that j is strictly greater than I, right? So do any of these quantities depend on xj? I'm taking the expectation with respect to, I've already taken out the expectation, right? I've already averaged these quantities out all the way from I plus 1 up to n. Okay, so this is not a function of xj for j strictly greater than I, because in both these terms I've averaged out with respect to xj for sure. So this quantity is basically equal to this quantity times expectation with respect to xj of this quantity. Right, so you should remember that this is now a function of x1 through xj. This is a function of x1 through xj minus 1. This is a function of x1 through xi, and this is a function of x1 through xi minus 1. So if we are taking the expectation with respect, so this is not a function of xj because j is strictly greater than I. This quantity is a function of xj. This is not a function of xj anymore. right? So the only quantity here, which is a function of xj, is this particular quantity, right? And what happens when I take expectation with respect to xj of this? What can I say about this particular quantity? This is just expectation of xj of delta j. And what have we just seen about this? This is equal to 0, right? Well, this is true for expectation with respect to xj. So what is expectation with respect to x1 through xj minus 1, xj plus 1 through xn? This is just expectation with respect to xn, right? When I write expectation with respect to n random variables, I can sort of sequentially take the expectation because they're all independent. But if not, I would have to sort of take conditional expectations. So what is expectation of xn with respect to xn of delta I delta j? It's equal to 0. So the delta I and so each delta I has 0 mean, and for j greater than I, delta I and delta j are uncorrelated, right? So that's useful because now if I go back to equation 1, what is the variance of z equal to? It's expectation of summation I equal to 1 to n of delta I squared. But again, I can use linearity of expectation. So from 1, the variance of z, or the variance of f of xn, is expected value of summation I equal to 1 to n delta I squared. But this is equal to expected summation I equal to 1 to n expectation of delta I squared. But I know that each delta I has 0 mean. So it's just the sum of the variances of the delta i's. So it's summation I equal to 1 to n variance of delta I. But if you look at each particular delta I, what does it effectively represent? Correct. So in some sense, the deviation of the ith variable from its mean, roughly speaking, right? Because each delta I is in fact a random variable. That's something to always keep in mind. Each delta I is a random variable that depends on x1 up to xi. But basically, it is the deviation of this function of x1 through xi, and how much it deviates from the average taken with respect to only xi. Correct? So it's effectively the sum of the variances of the influences of the ith random variable in some sense. Right? And this particular quantity will be extremely useful. So this in itself is not a very useful quantity to analyze, but now we'll see another sort of bound on the variance. So this, recall, is an exact expression, correct? And in fact, you can show that this quantity is equal to this even if x1 through xi are correlated. So at least by deriving this, we've made use of independence just because it made things more convenient. But in fact, you can show that this variance is equal to the sum of the variances of the delta i's, even if x1 through xn are not independent of each other. Okay. Right. And in fact, this in general holds not just for functions of n random variables, but more complicated sequences of random variables. So effectively all that we require is a sequence of random variables z1 up to zn. So there are two sequences of random variables to keep in mind, z1 up to zn and x1 up to xn. Right, and all we effectively require is that the expectation of zi with respect to conditioned on x1 up to xi put it in a slightly different way. So if I have the expectation of zi plus 1, the conditional expectation of zi plus 1 conditioned on x1 up to xi, if this is equal to zi, then such a sequence of random variables taken with respect to x1 through xn is called what is called a martingale. Okay, so if this is true for all I, we say that the sequence z1 up to zn is a martingale with respect to the sequence x1 up to xn. And as it turns out, if each zi is basically a function, it's the conditional expectation of f of x1 through xn given x1 through xi minus 1, then it automatically forms a martingale. But a martingale can in general be can be a random variable in itself, not just a function of x1 through xn, but it can be a more general random variable. As long as this property is satisfied, it's called a martingale. And for general martingales, it's possible to derive such bounds on the variance. Okay, but for now we will just restrict ourselves to IID random variables. But the only thing to keep in mind is that these tools are far more general and far more powerful. All right, so that's one particular property. So in fact, we will show the following. So it's called the Efron-Stein inequality. So suppose that I have x1 up to xn being independent, and have finite variance or bounded variance. And f is some function of these n random variables. Okay, let me use g instead. let's define z as g of x1 up to xn. Then we can write the variance, or we can derive a bound on the variance of z in the following form. So this turns out to be less than or equal to summation I equal to 1 to n of z minus the expectation with respect to xi of z the whole square. So it's a sum of variances, right? Note that, sorry, another expectation. Yep. So it's a sum of variances of random variables where each, let me call this yi, is equal to z minus expected value with respect to xi, just xi of z. So this is basically summation I equal to 1 to n variance of yi. It's taken with respect to all the xn. In fact, you only need to take the expectation with respect to all random variables except xi, because sorry, it's taken with respect to all of xn. Okay, but as it turns out, you can get some more bounds. So this quantity is also less than, or the variance of z is also less than or equal to, so for each I, define zi prime as g of x1 up to xi minus 1 xi prime. So I replace the ith random variable with an independent and identically distributed copy. Right? So it's a function of x1 through xn, but except the ith random variable, and basically you replace xi with an IID copy. Okay, that's how I define zi. So zi prime is a new random variable. And you can bound the variance of z is less than or equal to half of summation I equal to 1 to n expected value of zi minus zi prime the whole square, and it's also less than or equal to half summation I equal to 1 to n expected value of zi minus zi prime. If you just take the positive part of this whole square, I equal to 1 to n expected value of zi minus zi prime, just the negative part, squared. So the positive part is basically the maximum of, the positive part of some quantity alpha is the maximum of alpha and 0. So basically, if alpha is less than 0, then the positive part of alpha is 0. If alpha is greater than 0, then the positive part of alpha is alpha. Same for the negative part. The variance is also less than or equal to summation I equal to 1 to n of the minimum of expected value Sorry, there's a slight error here. All of these should just be z. So it's expectation of z minus, let me call this ui, the whole square, where this minimum is taken over all ui equal to functions of x1 through xi minus 1, xi plus 1 through xn. So each ui is a function of all the n random variables except the ith random variable xi. Okay. The reason why these expressions are more convenient is because now this variation is only with respect to xi, right? You're talking about the deviation of z from the mean taken with respect to just xi, an average with respect to xi. With the rest, so you're keeping the rest of the components the same, but you're only seeing the deviation with respect to the ith component, correct? And suppose that the function does not depend too much on one particular component, you can see that each of these is bounded by some constant, right? By the deviation with respect to I, just with respect to xi. So it's just the sum of the deviations with respect to just xi. So you get pretty nice bounds on the variance in terms of the variances of each of the individual components. Right? So in general, the Efron-Stein inequality is not the best possible inequality you can derive, but it's a very general case. In the most general case, yes, it is the best. But if you have more information about the function or the individual random variables, typically you can do better. But in problems where the function itself is like very complicated to analyze, or you do not have too much information on the individual random variables, this is the best possible that you can do. Right? So in the next class, we'll see some applications of the Efron-Stein inequality and see how to derive this. Right? So let's stop here for now. Just remember that tomorrow there'll be a quiz. So just like last time, it's going to be a pen and paper quiz for the first 25 minutes or so, followed by class. Let's stop.